Biology is the study of life. So you have to ask yourself, what is life? What is alive? At first glance, you think, well, I know what's alive. If something's moving, it's alive. My cat, it's alive, right? But what if something's not moving? Like this tree, it's not moving, is it? Maybe it is. Maybe if I look really closely and measure it over a long time period, I can see that it's actually moving, and then I can say, okay, it's definitely alive. But what about other things that aren't moving? Is this rock alive? It's not moving, but if I look really closely, maybe I'll see something that's moving. What if something moves but isn't alive? Like the wind or the river or my car. I don't think my car's alive, but it sure moves. Does it have to move to be alive? Does it have to be green to be alive? How do I know if I'm even alive? What about this wood? Maybe this wood used to be alive, but it's not alive anymore. If I was investigating, how would I be able to tell that? One of the big goals of the Mars 2020 rover and lander with Perseverance dropping down out of the sky is to find out if there's any evidence of life on Mars that's been there in the past, if there isn't any life now. By now we know that life comes in lots of different appearances. You know, it doesn't have to be green, it doesn't have to move, it doesn't have to be a certain size, it may even be microscopic, but we're going to use what we've learned from life on Earth to better understand what life could be like if we found it on Mars. A biosignature is a marker. A biosignature is like a footprint. It's evidence of life. Life that is existing now or is existing sometime in the past. Was existing sometime in the past. There are two ways to investigate biosignatures. We can look for chemical evidence or fossil evidence. Let's start with chemistry. Out of this entire periodic table, there are really just 6 elements that we focus on when we're looking for the possibility of life. CHNOPS. That's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. We've found all of these elements on Mars. Does that mean there's life on Mars? No. That just means that the basic building blocks to support life, for all life that we've known at this point, are there. It could happen. This is a piece of evidence leading towards a conclusion. H2O. This is water. Hydrogen and oxygen put together in a magic combination that makes delicious drinking water. But this is something that we know is necessary for all life on Earth. So if it's necessary for life, we have to find it somewhere else that we're looking for life too. At least if we're going to find life that we know. We have evidence of liquid water on Mars in the past. We have evidence of water still on Mars now in either frozen form or in super salty, briny liquid form. Another piece of evidence. Oxygen, O2. This is what we breathe. Oxygen is either something that a plant needs to get rid of or something that we need to breathe in. These are things that are very important to the life process. So they would be something that could be a biosignature, but then again, oxygen is something that is released from breaking down of other things that are not living. So it doesn't necessarily mean that something's alive, although finding oxygen could be an indicator. Plants and algae release oxygen, and I can see that they're alive because of the oxygen that they're releasing. My little jar of pond water here, I know there's living things in there because I can see bubbles of oxygen being released as it photosynthesizes. I can also see some of the tinier organisms wiggling around in the soil, and I know if I take some of the water and put it under the microscope, I can see other even smaller organisms wiggling around in the water. But that doesn't necessarily mean that all presence of oxygen means that things are just alive. However, 800 million years ago, the oxygen levels on Earth skyrocketed. Why did this happen? Well, we think that there was a large boom in the amount of photosynthesizing organisms that were suddenly releasing a large amount of oxygen into the atmosphere. We know that there wasn't a lot of oxygen in the atmosphere before that because the oceans used to be saturated in iron, dissolved iron particles just floating around in the ocean. And as these ocean particles were suddenly being in contact with more and more oxygen, that oxygen would bind to the iron and form iron oxide. That's rust. Rust would be sinking to the bottom of the oceans in layers and layers and layers, and we don't have that anymore. We don't have high levels of iron dissolved in the oceans, and we don't have that because there was so much oxygen that attached to the iron that took it out of the oceans. A sudden increase in the amount of oxygen oxygen is an indication of photosynthesis, and photosynthesis is something that's done by living organisms. CO2, carbon dioxide, is another one that's part of the process of cellular respiration, part of the process of photosynthesis. This is something that we could look to see if something was alive, although carbon dioxide is also released when you burn things. So carbon dioxide doesn't necessarily mean that it's evidence of life. We'll have to leave this one alone for a bit. Fractionation, this is a new word, a big word. Fractionation means that fractionation is a more complicated way of looking at the elements and the molecules that are in a rock. If you find that the elements and molecules are in a random pattern, that means it's probably not an organic process. It's not part of some living organism that was setting them out. But if you find that they are in a regular ratio, then there's more indication that there may have been a living process involved. Fossils. Fossils are another way of looking at the past, looking at evidence of life that used to be. When we think of fossils, usually we're thinking of something solid. We're thinking of maybe footprints, or like this is a fossil of an ammonite, an ancient sea creature, but this is no longer made out of shell. This is just stone. For a fossil to form, it needs to be buried and it needs to be protected from weathering. It needs to be protected from physical weathering, like wind and rain. It needs to be protected from chemical weathering, like oxygen that would bind to it and take its molecules apart. Fossils can be very large, but they can also be microscopic. Microscopic organisms can be fossilized also. Now we merge biology and geology. This is a fossil of one of the oldest rocks on Earth. 3.5 billion years ago. It's called a stromatolite. And it comes from a place in Western Australia where some of the oldest rocks on Earth have ever been found. Stromatolites are still around today. Not as many as there were back then, but they are still around, which gives us a good understanding of what they do, how they form, and how they live. This is how they work. The actual organism that creates stromatolites is called a cyanobacteria. This cyanobacteria, as it lives and grows, and it is going to reproduce, and it reproduces by dividing. So you have one cyanobacteria splits into 2 cyanobacteria, and then 2 cyanobacteria split into 4 cyanobacteria, and 4 bacteria split into 8 bacteria, and 8 bacteria split into 16 bacteria. So as it grows and divides and spreads out, it is making what's called a bacterial mat. We're going to represent this with some wet toilet paper. As this bacterial mat is growing and dividing, it lays itself out in a relatively shallow layer of water. So it's got access to the sunlight, and it's sitting there and they're happily photosynthesizing. As they photosynthesize and they go through their life cycle, they grow and they divide, and eventually they die. But while they're living, they're picking up sediment from the water around them. They're picking up little pieces of sand and things like that are getting stuck in there. And they get a new layer of cyanobacteria over the top of them, and then a new layer of cyanobacteria on top of them, and then a new layer of cyanobacteria on top of them. And they get thicker and thicker and thicker until you have these layers that you can see, which were the layers of cyanobacteria as they built up over many, many years. So a cyanobacteria is the organism that's doing the photosynthesis, and the stromatolite is the structure that it builds as it lives and grows in a community of many, many cyanobacteria. Now let's go back to Mars. Now the place we're going on Mars is called Jezero Crater, and it looks a little bit like this. It has uphill part and a downhill part. And a long time ago, a meteor crashed into the area. Smash. And then there was a river that carved a river valley across the top end of this, and it filled the basin of the crater with water, and then eventually water flowed out another river valley down the downhill part of the crater. Now, one thing that happens with erosion is when we are sending water down this river valley, we are picking up some of the clay and sediment that was up above here and washing it down into the crater. And we're making what's called a river delta. Delta is a triangle, so we're going to use this to represent that river delta. So the area looks like this. We have slope, crater, river, delta. Water flows in, and then water flows out. And this happened many times over many, many years. So we know that there's a lot of sediment that's building up. And if sediment is building up, it's a great place to look for fossils because anything that was living there in the shallow waters, like a cyanobacteria might like to live, would be buried over time in that river delta. Two things that make it the perfect place to look for microbe fossils. Number one, it had water. Number two, it was buried. If there was life on Mars, this would be a really great place to look for it. Have a great day, guys.